In this video, we will download the data file and spend some time inspecting the data, cleaning the data, visualizing the data in different ways. So here is the full URL to the data file. You can see it's a CSV file that stands for comma separated values. And it actually looks like this. This is not natively an Excel format file, but you can open it in Excel and it will look like this. So we see at the top are the different labels of the columns or the features. So we have acidity, volatile acidity, citric acid, and so on. And here are all the values, and then there's something like 1,500 rows or so. So there's lots and lots of data in this table. Now, you do not, first of all, you don't need to write down this URL. I have it printed for you in the helper code file for this video. So you can just copy paste it from the helper file. Now, you do not need to download this CSV file onto your computer. In fact, what you should do is use a Pandas method. So there's a method in Pandas, a Pandas function, that will allow you to automatically import data files from the web given a URL like this. And once you get that into Pandas, it's going to look something like this. So you see here are all the columns, here are the data values, and here I'm just describing the data. So you can see we have the count. So it's actually almost 1,600 rows. So there's lots and lots of lines in this data table. And you can see the mean, so the average for each of these columns, standard deviation, and so on. So lots of features, lots of information we have about all of these different data features of these wines. Now, once you've imported all of the data, you can print out some additional information. So what I'm showing here is each column, so fixed acidity, volatile acidity, and so on. And then I'm printing out the number of unique values in the entire data set in this column. So this is not the total number of columns. There's 1,600 columns in the, 1,600 rows in the data file. But for each of these columns, each of these data features, there are 96 unique values of fixed acidity, 143 unique values of volatile acidity, and so on, down to, we get to quality, and that has 6 unique values. And quality, in fact, is going to be the dependent variable. This is going to be the thing that we are trying to predict in later videos. But for now, you can just focus on this. This just tells you a little bit about how much differentiable information there is in these different columns. Okay, so this is another thing you want to do. And then you want to generate a bar plot that looks something like this of all the different columns. So this shows you the distribution of data values for all of the features and also the dependent variable that we have. Now you'll notice here that it looks like there's a couple of outliers here. There's a couple of data points that are very unusually large for total sulfur dioxide. Now, what I would like you to do is identify these points, or I should say the rows that contain these data points, and remove them from the data set. So we are considering these to be outliers or unusual values, and we want to identify which rows in the Pandas data frame contain these values and then get rid of them from the data set. And after you do this, then we want to explore the data visually in a few more ways. In particular, you can make a scatter plot, and here I'm using Seaborn to make this scatter plot, but it's not necessary to use Seaborn. And in this case, I'm showing residual sugar as a function of alcohol, but you can pick any two columns in the data set that you like. It doesn't have to be these two columns in particular, just to get a little bit of a sense of what the data look like. Okay, and then I would like you to make this plot. This will be the last plot for this video. This is called a pair plot, and it shows the, so you would select a couple of columns, and there's many, many columns, but for now, just pick 3 to produce a plot that looks like this. And this shows you the distributions of each of the plots, each of the variables here, so fixed acidity, volatile acidity, and citric acid, and all of the covariance across these sets of variables. So the relationship between volatile acidity and fixed acidity. Now, all of the colors, the individual distributions here, these densities, and all of these, the different colors here for the dots. These correspond to different quality values. So you can see the blue dots show the relationship between volatile acidity and citric acid for wines that have a quality rating of 3, and so on. So you might need to spend a little bit of time figuring out how to make this visualization in Pandas. All right, so it's quite a bit to do for this video, but it's all useful stuff, useful information, learning how to import data, work with data, remove outliers, and visualize data. So get started, pause the video, switch to Python, do some coding, get some graphs that look like what you see here, and then when you're ready, come back to the video, and now I will switch to Python and show you my solution. All right, so let's see, we also need Pandas, so I'm going to import Pandas as PD, and I'm going to use Seaborn a little bit for some of these nice graphics. So Seaborn as SNS, and well, later on in later videos, we're going to need the stats module from SciPy, but we don't have to worry about that for now. Okay, so here is the URL. And what I am going to do is say data equals, this is really straightforward, this is pretty easy, pd pandas dot read underscore CSV, and then the website name, the URL that we want to download the data from. And then let's just type data and have a look and see what this looks like. So it looks like we have 1600 rows, so that part matches what I said in the video, but 1 column. So that's, yeah, this is not what is going on here. Well, what's going on here is that CSV actually stands for comma separated. So in fact, this function is expecting to separate out the different columns according to commas, but there are no commas, there are semicolons. So we need to tell read CSV explicitly that the separator is equal to the semicolon, like this. So let's try this again. This looks much nicer. Now we see 12 columns and we get a bunch of normal looking values. And yeah, here's the labels for each column and so on. Here's the first couple of rows and the last couple of rows. So this looks good. And then there's another figure that I showed or screenshot that I showed, which was generated by data.describe. So this is a pretty useful function in the Pandas data frame. So if you just type data like this, or whatever the data frame name is, then that gives you, basically all of the data. And if it's a huge amount of data, then it will just show you the beginning and the end. Data.describe gives us a bunch of descriptive characteristics about all of the data, including the counts, the means, the standard deviations, and so on, maximum values, and these are the quartiles and so on. So, and then the next thing we were supposed to do is to print a list of unique values per column, or maybe we can call this per feature. So how do we go about doing this? Well, we can start by saying, let's start by looking at data.keys. This is going to give us a list of all of the column titles. So these are all the variable names that we have in our data set. So what we can do is grab all of the data from one of these keys. So let's say data, and I'll go for ph because that's the least number of characters to type. Okay, so this is just giving us all of the values in this column. Now what we want actually is the unique values. So numpy.unique, and this tells us all of the unique values. By the way, you could also do this by using a set, by converting this into a set. And a set object, or the set type, is going to ignore all of the repeats. So these are all of the unique values. They also happen to be sorted, which is an interesting thing to know about the unique function. But that's not relevant for now. Also, it's not actually relevant what these values are. We just want to know how many unique values there are. Okay, so we now know that there are 89 unique values out of a total of 1600 values in this column for pH. Okay, so this is one column. So what we need to do is loop over all of the columns. So I'm going to write for I in data.keys. And then actually, let me first just print out, I'll use f strings for this. So I'm just going to print out column, and then this is going to be I. So we're starting slow here just to make sure that, that we're getting the right thing. Okay, so column fixed acidity, and yeah, all of these different columns. So this is looking good. So has, and then we're going to put in something here, something unique values. And that is going to be, so what we need to place in here is something like this. Now it's not exactly this, of course, because this is hard-coded to one column. Nonetheless, I'm still going to run the code as is, even though I know this isn't correct. I just want to make sure I haven't made any silly typos, which apparently I have. And actually, the problem here is not a typo. The problem is that I have the single quotes here and the single quotes here. So Python, in fact, is thinking that this pH here is supposed to be a string that's grouped together with all of these other strings. So what I can do is replace the single quotes with double quotes. Okay, and now we didn't do the right thing, but we didn't get any errors. So that's good. We haven't made any syntax errors. So actually all we need to do now is replace pH with I, because I is looping over all of the keys. So this tells us each column and all of the unique values that are in each of those columns. Or actually it's not the unique values, but the number of unique values, of course. Okay, so the next thing I want to do is generate that big bar plot that I showed before. And we can say SNS dot, or boxplot actually, dot boxplots, and the data equal data, so it's pretty straightforward, and plt dot show. Let's see what that looks like. Okay, so it looks like chicken scratch, you know, like a bunch of chickens are on a farm in a desert, and there's all walking around over here. So what do we need to do? We need to make this be much, much, much wider so that we can actually see all of these column labels here. So to enforce this to be wider, I'm going to say fig, comma, x equals plt.subplots1. We just want one subplot. And what I really want to do is adjust the figure size. So let's try maybe 15 by 5. Let's see what that looks like. And then I need to specify that this is going to be plotted into the axis. Okay, this is looking a little bit better. I'll make this a little bit wider. Maybe 18 is good. Okay, so now the plot is getting good in terms of the size, but we still see some of these column labels are just pretty long. So I think it would look a bit better if we would rotate these by 45 degrees. In fact, that's what I also showed in the slides. So to do this, we are going to write x.set xtick labels, and then we want to specify that the rotation equals 45 for 45 degrees. So let's see what that does. And it gives us an error. It says missing required positional argument labels. So the problem here is that, in fact, this function here is expecting an input. It requires an input of the actual labels themselves. Now, here's the thing. I'm already happy with the labels we have. I don't want to change the labels. So there's a couple of ways that we could go about doing this. We could manually specify that the labels are the keys, like what we did here, the data keys for the column labels. But so that would be totally fine if you do it that way. I'm going to do it slightly differently. I'm actually going to get the existing labels and just put them right back into this function here. So to get the existing labels, I write x.get xtick labels. And then these are the labels that we're going to use. Okay, now this is looking better. And here we can see these two outliers. Looks like two. Sometimes, you know, when you're looking at these bar plots, it can happen that there are multiple data points lying on top of each other. So there's at least two data points that I'm going to consider an outlier. And I'm going to say that we can identify these outliers as any data point in this column, total sulfur dioxide, that is greater than 200. So I'm just going to call this the threshold. Of course, you could also call it a threshold of 250, or 232.17. That would also work. But I'll just go with 200 just for simplicity. So how do we identify those data points? Well, let's start just by looking at all the data from that column. So this is going to be total sulfur dioxide. And here we see all of those data. And then what I'm going to do is write greater than 200. And this is going to return a Boolean vector that is all false where the data are less than 200. And it's going to be true wherever the data are greater than 200. Now that doesn't, we don't see any trues in here because it's only a couple of data points out of 1600. So, the probability of the outliers being in the first five or the last, or the first five or last five is pretty small. So in fact, I'm going to turn this thing around and this is all going to be true. So now what I'm going to do is say data where this is true are the rows that we are going to keep. So notice that now this is 1598 rows. And then here we get 1597. And in fact, earlier we had, so let's see. So when we go up here, so there was 1599 and now it's down to 1597. So there were two rows. So it was actually just exactly two data points here. Okay, now this doesn't actually change the data. That's just printing out the data. So we need to reassign this data matrix to be itself, but only the rows where total sulfur dioxide has a value of less than 200. And that successfully removes those two outliers. In fact, maybe it's a good idea to rerun this plot here just to demonstrate. So now you can see, in fact, the y-axis scale has changed. So some of these other plots are a little bit more visible, and we don't see these two big outliers over here. There's nothing over 200. So moving right along. So what we want to do now is do a little bit of visual data exploration. So I'm going to start by creating a scatter plot where the x is going to correspond to the data, and I will use the residual sugar, this one, and set the y axis coordinate to be data alcohol, this one. All right, and then let's just have a look at this. Now with these scatter plots, you can make this pretty fancy. You can include a density function underlying here. You can add some marginal distributions and so on. I'm not going to do that now in this video because we're going to explore some additional visualizations and also just in the interest of time. And so let's see. So then what I want to do is move on to this pair plot. So we get this also using Seaborn. So seaborn.pair plot. And basically the way this works is you specify some number of columns in a list. So let's say we have alcohol, and I'll use pH because I happen to know that one is easy to write. It's really short. Okay, so let's see. Let's just try this right now with just a basic version. So here we have alcohol and pH. And you see the histogram of alcohol. So that's when you look at the co-distribution of alcohol and alcohol. And here's the co-distribution of pH and pH. And then the covariance, so the relationship between pH and alcohol, you see plotted here. And so you see it looks like there's some positive relationships here. Now there's a couple of additional inputs that I would like to add here. So I'm going to write kind equals reg, that's for regression. And that's going to additionally compute and plot these regression slopes with the confidence intervals around them. So there we can see, we can visualize the relationship between these pairs of variables a little bit better. And then we use the crucial keyword here is hue by, so hue is for color, by quality. And this is going to well, that's not going to work because quality is not actually in this input here. So we need to say quality. And then, so this is basically going to change the colors according to the values of quality. So now we see lots of distributions here and lots of sets of data points in here. And again, as I mentioned in the slides, this is basically broken up according to the different ratings of quality. So this is already pretty interesting. This one shows the alcohol, and we can see that green looks like it's low. So green and orange are fairly low. Those are low quality, and purple and brown are getting to be higher quality. So this is already pretty insightful that we see that the more alcohol there is in the wine, the more people rate it as high quality. That is not very surprising to me. Okay, so I want to make this slightly bigger, and therefore I'm going to actually soft code this a little bit. So let's move this up here. I will say another variable call, let's call this calls to plot equals, I want to show fixed acidity, and let's add citric acid, and let's just leave it at those guys for now. These are not all exactly the same values that I showed in the should be calls to plot in these slides, but that doesn't really matter. The point is not to show the exact relationships between any particular set of variables, more just illustrate to you the mechanism of generating this really useful plot for data exploration. Okay, and here we go. So it doesn't all fit on one screen, but if you're using it on your computer, you probably have it, you probably don't zoom in quite as much as I do. So it's pretty interesting to look at all these different variables and just try to see qualitatively if some of these relationships are changing as a function of the data quality.